If I showed you this, and you know little about neural networks, it might be hard to understand. So how about we simplify it? And focus on the core idea on how to train a model. I found very few simple examples online on how to train AI models. Many do show the machine learning code, but rarely do they explain how everything gets computed in a simplified way. So let me explain with a simple example where we'll have a model predict the weight and bias of a linear function. A neural network is a math function that learns patterns in data through trial and error, which is exactly what this code does. Models need a dataset to be trained on. This is our dataset with 4 data points. All x values are the inputs, and y is what the model should be predicting correctly at the end. Let's say we're calculating the final price of a taxi ride, where x is the amount of kilometers driven. If we drive 1 kilometer, then the final price is 3. If we drive 2 kilometers, then it'll be 5, and so on. Of course, we know that in this case, the linear function is y is equal to 2x plus 1. The weight is 2 and the bias is 1. But the model doesn't know that yet, it'll have to figure that out on its own. To visualize, this line represents the correct linear function, what we'll later call the target line. This creates the simplest possible model. PyTorch creates random starting values for both the weight and bias, usually somewhere between -1 and 1. Every time I run this code, the values will change to new random values. For demonstration purposes, I'm going to freeze the randomness, so the results will be the same on each run. The learning rate decides how big the updates are during training. A low rate means more accurate results, but it'll compute a lot slower. Higher rates will have the opposite effects. The kind of optimizer we're using is a stochastic gradient descent. This nudges the model settings a little each time it learns from the data. Model parameters tells the optimizer which parts of the model it should update. In our case, the weight and bias. This makes 10 equally spaced numbers from 0 to 5, where the view reshapes the tensor from a one-dimensional tensor to a two-dimensional tensor with 1 column. Plot figure creates a new plotting area with a width of 8 inches and a height of 6 inches. Next, we calculate the y values for the model's line using the random weight and bias. Then, using matplotlib's plot function, we draw a red dashed line with some thickness, labeling it for the legend. This does the same but plots the target line instead, later showing us how far off the model is from the right answer. This loop trains the model. Each iteration represents a full pass over the data. During an epoch, the model follows the same core steps: forward pass, loss calculation, backwards pass, weight update, and a reset of the gradient. Forward passing is just feeding our predefined x values into the model to calculate a prediction of y. During the first pass, the weight and bias are still random. To measure how wrong the model's predictions are, we compute the loss. This is done by subtracting the true values from the predictions, squaring the result, and then taking the mean. The final value represents the average prediction error. Let's print the loss. What's important here is the grad_fn. It tells PyTorch that this tensor knows how it was computed. Loss backwards doesn't use the numeric value of the loss itself. Instead, it uses the computation graph that PyTorch tracked through the grad_fn. Backpropagation then applies the chain rule to compute gradients. The chain rule is a way to find the derivative of a function that depends on another function. If that sounds confusing, then maybe the formula might help. I won't go into detail, but this is how everything is calculated. Once the gradients have been computed, we update the weights using the optimizer. Each weight is adjusted by multiplying the learning rate by the gradient, then subtracting that from the weight. This should create a new improved weight value. 0 grad clears all previously stored gradients, so the next backpropagation will start from scratch. No grad turns off gradient tracking, so PyTorch doesn't waste memory or compute unnecessary derivatives. We use this to calculate the new y values with the updated weight and bias, then plot the values. Each time we go to the next epoch, it will plot a new line, hopefully getting closer and closer to the target line each iteration. In the loop, I added some print information to give you a better understanding of the output. And lastly, some matplotlib functions to add naming and a legend to the graph. Let's run the code and have a look. We see the initial random weight and bias, and if you look closely, you'll start to notice that during each epoch, the line leads closer and closer to the black dashed target line. The more epochs and the lower the learning rate, the better the results. Of course, this is a very simple example, and quite an expensive taxi. I think I'll take the bike next time. I have a Gumroad, which will be linked in the description if you wish to support me, and if you have any questions, ask away. Alright, I'll see you next time.